Welcome to the fascinating world of remote sensing. In this video, we'll explore the fundamentals of how scientists and engineers gather information about our planet without making direct contact. Remote sensing combines art, science, and technology to record, measure, and interpret data from a distance, using sensors that detect energy patterns. Whether it's monitoring forests, tracking urban growth, or assessing natural disasters, remote sensing provides us with timely and reliable data. Let's embark on this journey to understand how remote sensing works, its core principles, and why it's so essential for modern resource management and environmental monitoring. Remote sensing is the process of obtaining reliable information about physical objects and the environment by recording and interpreting imagery and digital data from non-contact sensor systems. These systems capture radiation in various wavelengths reflected or emitted by Earth's surface features. The data can be recorded on film, as in aerial photography, or digitally for image generation. Remote sensing offers extensive, timely data on resources and the environment, supporting efficient resource management and national development. It's a powerful tool that helps us see the world in new ways, revealing patterns and changes invisible to the naked eye. Several critical elements work together in remote sensing. First, there's a source of illumination, usually the sun, which provides the electromagnetic energy needed. As this energy travels to and from the target, it interacts with the atmosphere, undergoing scattering, absorption, and refraction. When the energy reaches the Earth's surface, it interacts with various features depending on their properties. Sensors then detect and record the scattered or emitted energy, capturing detailed spatial data. Finally, this recorded energy is transmitted electronically to receiving stations where it's processed into usable images for analysis. As electromagnetic radiation travels from its source to the Earth's surface and back to the sensor, it encounters several obstacles. The atmosphere modifies its path through scattering, absorption, and refraction, which not only changes the radiation direction but also provides valuable atmospheric data. The energy then interacts with the target, and the nature of this interaction depends on both the target's properties and the radiation's characteristics. The sensor records the scattered or emitted energy, which is then transmitted to a processing station for image creation and analysis. Once the energy reaches the target and interacts with it, the sensor detects and records the electromagnetic radiation that is scattered or emitted. This data is then transmitted electronically to a receiving and processing station. Here, the information is processed into images that can be analyzed for various applications. This entire process, from energy emission to data processing, is what makes remote sensing such a powerful tool for observing and understanding our planet. Remote sensing relies on two main types of sensors: passive and active. Passive sensors detect natural energy such as sunlight that is reflected or emitted by objects on Earth. They are commonly used for capturing images in visible and infrared wavelengths. Active sensors, on the other hand, generate their own energy, such as radar or sonar signals, and measure the energy that is reflected back from the target. This allows them to operate even in the absence of sunlight, making them useful for nighttime or all-weather observations. Passive sensors are perhaps the most familiar type in remote sensing. They rely on natural sources of energy, primarily sunlight, to illuminate the objects or scenes being observed. The sensors then detect the energy that is reflected or emitted by these objects. This method is widely used in satellite imagery and aerial photography, capturing detailed information about Earth's surface in various wavelengths, especially in the visible and infrared region. Active sensors take a different approach by emitting their own energy towards the target, and then measuring the energy that is reflected or scattered back. Examples include radar and sonar systems. These sensors are particularly valuable because they can operate independently of sunlight, making them ideal for nighttime or cloudy conditions. Active sensors provide their own source of illumination, ensuring consistent data collection regardless of environmental lighting. Electromagnetic radiation, or EMR, is the foundation of remote sensing. It refers to all energy that moves at the speed of light in the form of waves. The sun is the primary source of EMR, which travels through space and interacts with objects on Earth. The characteristics of EMR, such as wavelength and frequency, determine how it is reflected, absorbed, or transmitted by different materials. Understanding these properties is crucial for interpreting remote sensing data. Wavelength of electromagnetic radiation is a key factor in remote sensing. It is defined as the distance between successive wave peaks and is usually represented by the Greek letter lambda. Different wavelengths interact with materials in unique ways, influencing how energy is reflected or absorbed. This is why sensors are designed to detect specific wavelength ranges, allowing them to capture detailed information about various features on Earth. Electromagnetic spectrum encompasses the entire range of electromagnetic radiation, from gamma rays to radio waves. In remote sensing, different regions of the spectrum are used for different purposes. Ultraviolet radiation has shorter wavelengths than violet, while infrared has longer wavelengths than red. Each region provides unique information, and understanding the spectrum is essential for selecting the right sensors and interpreting the data they collect. Gamma rays and X-rays occupy the shortest wavelengths in the electromagnetic spectrum. Due to atmospheric opacity, they are rarely used in remote sensing except for specialized applications, such as detecting radioactive materials or studying airless planetary bodies like the Moon. These wavelengths are primarily utilized in low-altitude aircraft observations or for scientific research beyond Earth's atmosphere. Ultraviolet region is mainly used for studying planetary atmospheres or airless surfaces, as Earth's atmosphere blocks most ultraviolet radiation. The visible region, however, is crucial for remote sensing. It receives the most solar illumination and is easily detected by sensors. This region is associated with color perception, covering blue, green, and red wavelengths, and is essential for creating true color images of Earth's surface. Infrared region of the electromagnetic spectrum is divided into several subregions: reflected, thermal, and far infrared. Near-infrared and short-wave infrared are important for vegetation and soil studies, while thermal infrared provides information about surface temperature. Far infrared is influenced by molecular rotation and vibration. These regions are used by various remote sensing instruments such as imagers, spectrometers, and radiometers to gather detailed environmental data. Microwave radiation, with wavelengths from 1 to 1 m, is widely used in remote sensing for radar systems and microwave radiometry. It can penetrate clouds and is less affected by atmospheric conditions, making it ideal for all-weather observations. The radio wave region, with wavelengths greater than 10 cm, is used by active sensors like imaging radars and altimeters, as well as passive radiometers for environmental monitoring. As electromagnetic radiation travels through the atmosphere, it is affected by various processes. Scattering causes the radiation to change direction unpredictably, while absorption by atmospheric gases reduces its intensity. Refraction bends the radiation as it passes through different media, and attenuation is the combined effect of absorption and scattering, resulting in energy loss. These atmospheric effects must be considered when interpreting remote sensing data. Scattering in the atmosphere can be elastic or inelastic. Elastic scattering, such as Rayleigh-Meilland non-selective scattering, does not change the energy of the radiation. Inelastic scattering, like Compton and Raman scattering, involves a change in energy. Understanding these types of scattering helps scientists interpret the signals received by remote sensors and correct for atmospheric effects. When electromagnetic energy reaches the Earth's surface, it can be reflected, absorbed, or transmitted. The proportions of each interaction depend on the material's properties, condition, and the wavelength of the radiation. These differences allow remote sensing systems to distinguish between various features in an image. Understanding how energy interacts with different surfaces is key to accurate interpretation of remote sensing data. Incident energy on a surface is divided into three parts: reflected, absorbed, and transmitted. The amount of energy reflected, absorbed, or transmitted varies with the type of material and the wavelength. For example, some features may look similar in one spectral range but very different in another. This is why understanding reflectance properties is so important in remote sensing, especially for identifying specific features in an image. Reflectance is the ratio of reflected light to incident light. It can be specular like a mirror or diffuse like a rough surface. In remote sensing, diffuse reflectance is most important because it contains spectral information, or the color of the reflecting surface. Specular reflection, on the other hand, appears bright or dark but lacks color information. Understanding these differences helps in interpreting remote sensing images accurately. Specular reflectors, like calm water or smooth surfaces, reflect light in a single direction, creating mirror-like images. Diffuse reflectors, such as rough surfaces, scatter light in all directions, providing more spectral information. In remote sensing, diffuse reflection is crucial because it reveals the true color and composition of the surface, which is essential for accurate analysis and classification of features. Spectral reflection curve shows how much energy is reflected by an object at different wavelengths. These curves are unique for different materials, such as water, vegetation, and soil. For example, vegetation reflects strongly in the near-infrared region, while soil has greater reflectance in the intermediate infrared. Water is primarily identified using visible and near-infrared wavelengths due to its low reflectance. These curves help scientists distinguish between different features in remote sensing images. Soil reflectance is influenced by several factors, including moisture, texture, roughness, mineral content, and organic matter. Coarse, sandy soils with low moisture reflect more energy, while fine-textured, poorly drained soils reflect less. Organic matter and roughness also reduce reflectance. Iron oxide in soil lowers reflectance in the visible spectrum. These variations help remote sensing systems distinguish between different soil types and conditions. Vegetation reflectance is determined by leaf pigments, structure, and moisture content. Healthy plants absorb blue and red light and reflect green, making them appear green to our eyes. In the near-infrared region, reflectance is influenced by leaf structure and varies across species. This makes near-infrared data valuable for identifying plant species and detecting stress. Water absorption bands and peak reflectance points provide additional information for monitoring vegetation health. Water interacts with electromagnetic radiation in unique ways. Its surface mainly produces specular reflection, while deep, clear water absorbs most near-infrared energy, acting like a blackbody. Suspended materials increase reflectance, and high chlorophyll concentrations affect the blue and green regions. Remote sensing uses these properties to monitor water quality and algae. Snow and clouds can also be distinguished using visible and mid-infrared wavelengths. Platforms are the stages where sensors are mounted to collect data about targets. Based on altitude, platforms are classified as ground-borne, airborne, or spaceborne. Ground-borne platforms use tripods, buildings, or vehicles for close-range sensing. Airborne platforms, such as aircraft, offer flexible altitude and timely data collection. Spaceborne platforms, like satellites, provide high-speed, global coverage and continuous observation of Earth's surface. Ground-borne remote sensing involves sensors placed close to the ground, using tripods, buildings, handheld devices, or moving vehicles. This method allows for detailed, high-resolution data collection and is often used for calibration, validation, or specialized studies. While it covers smaller areas compared to airborne or spaceborne platforms, it provides valuable, precise information about specific targets. Airborne remote sensing uses aircraft, and historically even pigeons, balloons, or kites, to carry sensors at various altitudes. This approach offers flexibility in data collection, allowing for timely and targeted observations. Airborne platforms are ideal for regional studies, disaster monitoring, and mapping projects that require higher resolution than satellites can provide. Spaceborne remote sensing involves mounting sensors on satellites that orbit the Earth. These satellites provide high-speed, continuous global coverage, making them essential for large-scale environmental monitoring, weather forecasting, and resource management. Spaceborne platforms can observe vast and remote areas, delivering data that is otherwise difficult or impossible to obtain. Resolution is a key concept in remote sensing, referring to a sensor's ability to distinguish between closely spaced objects or signals. It determines the level of detail in an image and is defined by the smallest separable unit the sensor can detect. There are four main types of resolution: spatial, spectral, radiometric, and temporal. Each type plays a unique role in how data is captured and interpreted. Spatial resolution refers to the size of the smallest object that can be distinguished in an image, usually measured in meters per pixel. Very high-resolution sensors can detect objects smaller than 1 meter, while low-resolution sensors capture larger features. The choice of spatial resolution depends on the application, with higher resolution needed for detailed mapping and lower resolution for broader studies. Spectral resolution defines the specific wavelength intervals a sensor can record. Sensors with high spectral resolution can distinguish between narrow bands of the electromagnetic spectrum, allowing for detailed analysis of materials and features. This is especially important for applications like mineral exploration, vegetation studies, and water quality assessment. Radiometric resolution refers to the number of digital levels used to express the data collected by a sensor. The higher the radiometric resolution, the more detail can be captured in the image. For example, an 8-bit sensor can record 256 levels of brightness, while a 6-bit sensor records only 64. This increased detail is crucial for detecting subtle differences in features and condition. Temporal resolution is the frequency with which a sensor can revisit and collect data from the same area. High temporal resolution means more frequent observations, which is important for monitoring changes over time, such as vegetation growth, urban expansion, or disaster recovery. Different satellites have different revisit periods, ranging from a few days to several weeks. One of the greatest advantages of remote sensing is its ability to cover large and often inaccessible areas. This makes it possible to monitor vast regions such as forests, deserts, or disaster zones that would be difficult or dangerous to reach using traditional methods. Remote sensing provides a bird's-eye view, enabling comprehensive analysis and decision-making. Remote sensing enables both temporal and spatial analysis. By collecting data at regular intervals, scientists can track changes over time, such as deforestation, urbanization, or climate impacts. High spatial resolution allows for detailed mapping and precise analysis, supporting a wide range of environmental and resource management applications. Environmental monitoring is a major application of remote sensing. It allows for the tracking of deforestation, pollution, and the effects of climate change on ecosystems. By analyzing satellite images over time, scientists can assess the health of forests, monitor water quality, and detect changes in land use, providing valuable information for conservation and policymaking. Remote sensing plays a vital role in agriculture by assessing crop health, estimating yields, and identifying irrigation or fertilization needs. By analyzing reflectance data, farmers and researchers can detect plant stress, monitor growth stages, and optimize resource use, leading to increased productivity and sustainability. In disaster management, remote sensing provides real-time data for damage assessment and emergency response. Satellite images help authorities monitor floods, earthquakes, wildfires, and other natural disasters, enabling rapid decision-making and efficient allocation of resources for rescue and recovery operations. Remote sensing supports infrastructure monitoring by providing up-to-date images of roads, bridges, pipelines, and other critical assets. This proactive approach helps detect potential issues, plan maintenance, and ensure the safety and reliability of essential infrastructure, reducing the risk of unexpected failures. Geological surveying with remote sensing allows scientists to investigate Earth's geological features without on-site exploration. By analyzing spectral data, researchers can identify rock types, mineral deposits, and structural features, supporting resource exploration and hazard assessment in a cost-effective and efficient manner. Urban planners use remote sensing to analyze city growth, land use, and infrastructure development. High-resolution images provide detailed information for mapping, zoning, and planning new developments, helping cities grow sustainably and efficiently while minimizing environmental impact. Remote sensing offers numerous advantages, including wide area coverage, accessibility to remote or hazardous locations, rapid data acquisition, and the ability to monitor changes over time. Its diverse applications span environmental monitoring, agriculture, disaster management, infrastructure, geology, and urban planning, making it an indispensable tool for modern science and society. Deepen your understanding of remote sensing. There are many excellent resources available. Books like Introductory Digital Image Processing by John R. Jensen and Remote Sensing and Image Interpretation by Lillesand and Kiefer provide comprehensive overviews. Online resources from government agencies and educational websites also offer tutorials, case studies, and interactive tools to help you explore remote sensing further. Remote sensing continues to evolve, with advances in sensor technology, data processing, and applications. As we face global challenges like climate change, resource management, and urbanization, remote sensing will play an increasingly vital role in providing the data and insights needed for informed decision-making. By understanding the fundamentals, you're now equipped to appreciate the power and potential of remote sensing in shaping our world.